Today we're going to discuss fiber optics and the cables that transmit the signal. You'll notice here that a fiber optic cable consists of a core, cladding, and a jacket. This means that the light travels through this core, the cladding protects that core, and the jacket seals in the light. When light travels through this cable, it doesn't travel straight through as you would think. When light enters this, it goes on an angle, bounces, and keeps bouncing, bouncing, bouncing. Now the actual cable is of this size. Now you can see that there's a small cable of fiber inside, and here's the core lighting up now, and that's covered again by the cladding and the jacket. So light travels through this very, very easily, and that's why it's so used in communications. Here is shown we have one fiber optic cable that's carrying one signal. Here we're carrying 48 signals within the one cable itself. This means that we can communicate with 48 different devices. As we look, the core is covered by cladding and a jacket, and it's single fiber is what we looked at. The unique part about fiber optics is we can take, in this case, this one is carrying 36 various cores, so we can contact 36 different devices. And you can see that's still very small, but here's 48 devices, and now we go to 64. So in a very small, confined area, we can put many contacts through this one fiber cable. One of the things shown is this is a separate piece of fiber cable that has no jacket, and you'll notice that even at that, we still can get that light on the tip. Now that is used by manufacturers of holiday Christmas trees. Example, the trees that you see and often in the malls they're selling that turn colors, and all of the tips are different colors. Inside this tree is a rotating color wheel with different color bulbs, but all of these are manufactured with these little clear fibers that look like little whiskers, and they light up as soon as they're touched by some sort of a light source. These are all cut off. These are actually cut-offs from other products that are used by the manufacturer of these trees. The fiber cables depend upon what's known as an intensifier. The intensifier is the object that creates the infrared signal. The same as the infrared sensor, there's a sensitivity switch on the back so that we can make it either more sensitive or less. On the front side, you'll notice two portholes showing, and that's where the cables will connect in order to be operational. Now, as you can see, the intensifier has been powered up and there's an infrared signal being sent out. We will connect one of the reflective cables into that sender and one to the receiver, and then we'll lock the cables in place. Now that they're locked in place, we're able to show that we can detect an item that is coming into the field of the reflective sensor. The second mode of fiber optics are called true beams. You'll notice that each one of these are separate in itself, so one cable for one lens versus the reflective. True beams are used across on a conveyor system so that as a package or an object passes through, it will then activate. Now we'll connect this the same way that we did with the other, placing the cables into the intensifier. And once we have those connected, we now have a field shown here with the true beams looking at each other, a sender and a receiver. So as something passes through, it will see the object. Now, this can be done two different ways. This way, we're showing that when it sees the object, it will activate. However, we can change the mode of the operation so that when something is present, it actually stays off. So if somebody were to remove this, you would get a signal. This would be typical of a security system where you're guarding something or you don't want something removed, but if it does, it activates. The third mode of fiber optics classification would be called retroreflective. It's referred to as retro because we're using here a reflector, industrial reflector, with a reflective lens. So it's basically sending out one signal to this, and it's receiving back approximately 1,000 returns. So the advantage of this is used in automation, especially by places like UPS, to say that when only certain packages pass through, will you push them off the line. Let's give you an example of how that would work. If I cover part of this reflector, you'll see nothing happens. If I cover more of it, nothing happens. But if I cover it completely, it sends off a signal. So think of it this way. Small packages can pass through as long as they don't cover everything, as long as they don't cover the whole thing. But as soon as one covers everything, then it will take and send the signal. A typical application for a reflective fiber optic sensor is that of part recognition. In this particular case, this is attached to a rotary actuator. So when it sees the part, it's going to rotate, and it's going to hold it in a specific position for a given time, and then it's going to return. So the sensor itself is saying, I see the part, I will turn it around, and then I'll return it when it's all done. So you can imagine that this might be a paint spraying application or even a drilling application that we have to turn the part so it gets both sides finished. Once a part is done, it's taken out and it resets itself for the next part. And it'll do the exact same thing over and over and over. This will be accurate within 1/1000th of an inch every time it operates. So it's a very accurate system. This is a typical TrueBeam application. You'll notice that we have the sending device is starting out here. It is going to a mirror, from one mirror to the other mirror to the receiver over here. This is made so that if anything happens to come into this area, it will send off the alarm. So therefore, we've created a security light system all the way around the platform. By inverting the signal of our TrueBeam application, we now have a part that is set in the center of the platform. And assuming that that's a very valuable piece, if it's removed, it will set off the alarm.